All right, recording is rolling. So today I'm going to have you guys calculate a spring constant using conservation of energy, and we're going to be outside most of today. You guys remember these ball launchers from back when we were doing projectiles? You guys remember that? So these are back. These are out on the desk. There's also this ramrod, and there's a new kind of ball because we were short on the other one. So I bought a whole bag of these bouncy balls. Now, guys, technical detail. Is everybody paying attention right now? Because super important technical detail. Before, what I told you guys to do was to load the ball and then take the ramrod and ram it down. Okay, guys, don't do that. Don't do that. Here's why. This new kind of ball will get stuck in here, and it's a pain to get out. Okay, so what you want to do instead is first, don't load the ball yet. First, put it in the ramrod and actually, I have to release this thing. Go click, click, click. Right, so when it clicks a few times, right? And after you do that, then put in the ball. Okay, like that? Right. Okay? Right, so guys, what are you gonna do first? Are you gonna put in the ball first and then ramrod it, or are you gonna ramrod first and then put in the ball? Ramrod. Okay, so everybody got that? Alright, that will save you a bunch of trouble today. Alright. Now, I wonder, there, you guys can see it, picture on the outside, what's going on. You guys see the spring right here? Isn't this thing spring loaded with a lot of spring potential energy? Right? Right. So how could you maybe take advantage of conservation of energy to calculate what the spring constant is? Like how stiff is that spring? You guys on your desk should have a quarter page. You guys have a quarter page like this? Okay. Number it. Put your name at the top. So name at the top. Right. And then number it 1 through 8. Okay. So name at the top, then 1 through 8. Okay. So this is going to be a different kind of lab. I'm just trying something a little bit different today. Okay. And there's different ways that you can use conservation of energy to calculate spring constant. I've given you guys a printed page that has 2 possible procedures. Now, I only printed out about 10 or 12 of these, and I put them in plastic sleeves and put them around on the desk. So, guys, when we eventually go outside, you guys know that there are multiple parts of this lab, and make sure that you and your teammates collectively have some directions. There's a page that looks like this. There's about 10 or 12 of these pages around the desk. There's also a launcher. There's also a ramrod that goes with the launcher. There's also a bouncy ball. There's also meter sticks. Meter sticks can be important. Okay. I know there's a lot of equipment, but it's all out there. Just make sure you and your teammates have some of all stuff. Okay. So how are you going to get the spring constant? Right, so there's 1 of 2 setups you can do. You don't have to do both of these. Just pick your favorite one. Right? But I'll take you guys through both of these before we go out there. Okay? So one option is you could be on top of this ledge, and you could aim it straight horizontal and go boing. And if you measure this height, and you measure how far the ball goes, then that's one setup. Some of you guys did this before. In fact, if you did do this before, when we did projectiles, do you guys happen to remember how tall that ledge is out there, that balcony? I want to say it was like 4.5 meters, something like that. There is another set you could do, and this one's actually a little bit more straightforward. You guys will see when it shows. Is you can just aim it straight up and say what is the maximum height it goes to. Right? So either way, you could eventually figure out what the spring constant is. Right? But what are all the middle steps? Right? So you're going to have to know some numbers, like for example, gravity field. Oh, see where it says number 1 on either procedure, right? So when you guys get together with your teammates, figure out whether you want to do this via kinetic energy, which is the setup, or via potential energy, like height change, which is the setup. Right? And then next to number 1, write value for gravity, meters per second squared. And here's why that's going to be important. What if you took this whole project to the moon, where gravity is very weak? What do you think would happen to this distance d on the setup on the left? Would it be greater than, less than, or the same as on Earth? Greater. It would have to be greater on the moon, wouldn't it? Okay. Thank you. Does that make sense? Right. Okay, so gravity is really important. And what about if you do this setup instead? Then on the moon, what would happen to H? It'd also be much bigger on the moon, wouldn't it? Right. So pick your favorite, either 9.8 or 10 meters per second squared, and next to number 1 on this quarter page, write that number. So for example, I just picked 1 and wrote that. Okay. So many meters per second squared. Okay, guys got that? Question number 2, the mass of the ball. Now, why would mass be important? Well, think about this. What if you're using that spring launcher to launch a little tiny marble versus a big old bowling ball? What do you think this distance D on the setup on the left would be for the bowling ball? Very large, very small compared to the marble. Very small for the bowling ball, right? And then what about the height? If you use the bowling ball, you think it's probably not going to go that high, right? Now, I know this last week a lot of times mass cancels out, but it doesn't whenever spring is involved, and the spring is involved here, so mass is going to be important. So what is the mass of this bouncy ball? So I measured this ahead of time because y'all have basically the same. Well, they're all about 6.4 grams. So next to number 2. Now, guys, do you want to write the number 6.4? No, because you want everything to be in kilograms. So you guys do know that that's, well, to go from grams to kilograms, you divide by what? 1,000. Yeah, 1,000. Okay. I was thinking, the balls are a little bit different. Some are like 6.35 or 6.45, but they're all like in that ballpark, about 6.4. So if you use that number, you'll get something that's pretty close enough. Okay. Guys good so far? Okay, so even before we go out there, you guys have already got a couple of numbers, but I'm going to give you guys one more number just to help you guys out a bit, and that's the spring compressions. Because however much you compress the spring, like the more you compress it, the more energy it's stored. Okay. Hey, see if you guys remember this. 1/2 kx squared. You guys remember 1/2 kx squared? If you compress it twice as much, is that twice the energy? No, it's how many times the energy? 4 times. What if you compress it 3 times as much? How much energy? 9 times the energy. Okay. Now, what is the spring compression? Or compression distance. So I'll do this with you guys right now since everybody has the same launchers. Okay. So one way you do this is put the ramrod in, okay, right there. Then I'm going to take this pencil. I'm going to make a little mark on the ramrod right at this point. Okay. Then ram this all the way in. 1, 2, 3 clicks. It goes to this Velcro part. Okay. Then pull this out, and let me get the that difference in distance. Okay. So that's going to be looking at 7.3 centimeters. Okay, 7.3 centimeters. Okay. Now, do you want to write down the number 7.3? No, because that's in centimeters, not meters, right? You guys want meters? How many meters is 7.3 centimeters equal to? Roll back the decimal 2 places. You guys know 100 cents in a dollar, right? So that's 2 decimal places, right? Okay. Now, why did I put that on number 5? That's actually following the procedure for this one on the left. Okay. I'll take you guys through the rest of the procedure. Those are some of the starting values that are going to be good to know going out there. Okay. But how does this work exactly? Right. So set up on the left, where you're on top of the ledge firing horizontally. Why did I say that's via kinetic energy? Well, because the conservation of energy would go like this. The energy starts in the spring, right? Spring loaded. Right? And remember all these conservation of energy setups were going from some initial point to some final point. I bet a lot of you guys are tempted to pick this landing spot as the final point, but that's actually a very complicated way to do it. The simple way to do it is actually go initial point is spring loaded. The final point is right when it's leaving the cannon barrel. And I'll tell you guys why. Because right when it's leaving the cannon barrel, all of its energy is what kind of energy? Kinetic. So you're going from 1/2 kx squared to 1/2 mv squared, right? And if only you could figure out what that v is. Oh, well, isn't that this distance divided by the time? Right? And the time of fall, remember back to projectiles, is that related to this height? Right? H equals 1/2 gt squared. Right? Now, I helped you guys out a bit. So suppose you pick this procedure. I'll take you guys through it. So gravity, so many meters per second squared, mass, so many kilograms, boom, boom, got those done. With the meter stick, measure the height of fall. Okay. Yeah, I want to say it was like 4.5 meters, something like that, but you guys can double check that. Okay. What's the time of fall? Now this, you calculate the time. 1/2 gt squared, this goes back a few units, right? You can calculate t, but it did the algebra for you guys there. Okay. Then flip over on the back, this continues, we're still on the left column. Right. With the ruler, measure the compression distance, number 5. Oh, but we did that already. Remember, it was 7.3 centimeters, or 0.073 meters, right? Isn't that? aim launcher horizontally, fire the ball, measure the horizontal displacement in meters, that's this D, right? Then, wouldn't the blast speed have to be that distance divided by the fall time that you calculated from before? Okay, so you can get that, the speed, right? Oh, and then here's your conservation of energy setup. The energy that was stored in the spring all goes into kinetic energy, and at this point, the fact that you calculated that speed, look what you have. You know the spring compression distance, because I just measured that with you guys right now, about 7.3 centimeters. You guys know the mass of the ball, because I measured that ahead of time, that was so many grams, 6.4 grams, but plug in kilograms, of course. You guys know, you would at this point in the lab know what the speed is, because you would have gotten this for number 7, right? So isn't just K left to be found using algebra, right? And if you want to be really fancy about it, it's all in terms of exact measured variables. It looks like this, but I mean, if you've done all the middle steps along the way, then you don't necessarily have to do that. Right? You get spring constant in so many newtons per meter. That's how you measure spring stiffness, right? Okay. The other option you could do, which is actually a bit more straightforward, you can already see that because the one I just showed you guys has 8 steps, but the other way has only 5 steps, okay? Is you could aim this straight up in the air. Now it starts off same way, you know, gravity field, mass of the ball. Now this one, number 3 says the spring compression distance. So if you opt for this one, you can just put that value on number 3. Okay. Launch the ball and find the maximum height. Then grab the maximum height with the meter stick. You guys see those meter sticks around the room? Right, meter stick would be for either procedure. So make sure your teammates have a meter stick. Right? How many meters tall does it go? And then you can go straight to conservation of energy, but it looks a little bit different setup. So the energy from the spring, 1/2 kx squared, all goes into gravitational potential energy, energy of height, MGH. You guys see that? Okay. And then you could just solve K that way. It's a little bit more direct to do that way. Okay. Right. Any questions? Any questions? Right, so you guys got your name on this quarter page. You have it numbered 1 through 8, although if you pick that other procedure, you really have 5 steps, so that's okay too. Right? And at the very end, you'll have a conclusion. Spring constant equals so many newtons per meter. Right, you guys ready to head outside? All right, let's head outside.